Let's solve one problem using block diagram reduction technique. So question number 1, reduce the block diagram given and find C by R. C is the output and this R is the input. So C by R means it's output by input. So this is the overall transfer function of this particular block diagram. Okay. So now when you look first to the block diagram, you will feel like okay, we can combine these two blocks G1 and G2. Okay, so you will feel like okay, we can apply the rule of cascading these two blocks. In this case it is not possible, so it will be wrong to do such a cascading. Why? Because in between these two blocks we are having a branch point. So as long as this branch point exists over here, we cannot apply the cascading rule. So in order to apply the cascading rule, you have to shift this branch point either ahead of G2 or before G1 to this side. Okay, then you will also feel like okay, we are having G1 and H as a negative feedback loop. Okay, this is feedback. So from output side to the input side, it's a feedback, and the sign is minus here. That means it's a negative feedback. You may also think like okay, we can reduce this particular area because it forms a negative feedback loop. Definitely you cannot reduce this area. Why? Because again you are having a branch point over here. So as long as this branch point exists here, you cannot apply the rule for reducing this loop. Again, in order to apply that negative feedback loop reduction, you have to shift this branch point somewhere here. Then only you will be able to apply the rule. Okay, so we have two options. So either after shifting this branch point, you can go for this cascading and proceed, or else we can shift this branch point to this area and we can have a feedback reduction or feedback elimination. Okay, so right now in step 1 I am going to shift this branch point ahead of G1. Okay, so when I shift this branch point ahead of G1, some change or some modification should happen in this G3. Why? Because suppose the output of this summing point, let it be Y. Just an assumption. Assume that it's Y. If that is the case, then this Y signal is going to G3. Right? So signal Y, which is the output of the summing point, goes to G3. So that is the real case or the original case. But what will happen if I shift this branch point ahead of G1? Let's imagine that this branch point is now here. Then what is the signal that is going to G3? So that would be the signal coming from this G1 block. Okay, right? So the output of the summing point is Y, then that Y will pass through G1 and the output of this G1 will become YG1. Right? So right now that YG1 is moving to G3. But what should be the signal that should flow to G3? It should be Y only. But now as a result of shifting this branch point ahead of G1, the signal that is moving to G3 is YG1. So instead of that YG1, the signal should be Y. So how to obtain Y from YG1? Definitely YG1 by G1. Right? So we have to divide by G1. So that divided by G1 should be applied to this block. So instead of this G3, if I shift this branch point to this point, the G3 gain will now become G3 by G1. Yes. So I have shifted branch point from this point to ahead of G1. If that is the case, then the G3 gain will become G3 by G1. Okay, right? So now we can see that this is a perfect negative feedback loop. So now we can directly eliminate this negative feedback loop. So when eliminating this negative feedback loop, so what would be the overall transfer function of the single block? So when we eliminate this feedback loop, we'll be having only a single block. This will be converted into a single block with gain. So what would be the gain of that single block? It would be G1 divided by 1 plus G1H. G1 by 1 plus G1H. See this one, G1 by 1 plus G1H. Right? So after applying that, we can see here we are having two blocks in parallel. See, this is feed forward. Look at the direction of the signal. It is from input side to output side. So it's feed forward. It's not feedback. So I am having a block with the gain G2 and another block with the gain G3 by G1 in parallel. So this area can be reduced to a single block, and the gain of that single block will be G3 by G1 plus G2. G3 by G1 plus G2. Right? So now if you look at this particular diagram, you can see these two blocks are in series or two blocks in cascade. Now we can combine these two blocks into a single block. Then what would be the gain of that single block? If you are having two blocks in cascade, then we have to multiply the individual gains. So if we convert these two blocks to a single block, then the gain of that single block would be this G1 by 1 plus G1H into G3 by G1 plus G2. We have to simplify that. So G1 by 1 plus G1 into this is simplified by using this LCM. So this will become G3 plus G1 G2 by G1. So when we multiply these two terms, G1 will get cancelled, and what is remaining would be G3 plus G1 G2 by 1 plus G1H. So finally the complete system is reduced to a single block with the gain this G3 plus G1 G2 by 1 plus G1H. R is the input to the block and C is the output. So what is C by R? C by R would be the gain in this particular block, which is G3 plus G1 G2 by 1 plus G1H. So that is the overall transfer function of the given system. Okay, this is how we apply the rules of block diagram reduction technique, and this is how we find the overall transfer function of a given system. Okay.